In this video, we will summarize the formation of our solar system as currently understood through the nebular theory. Recall that a successful formation theory must explain four major features of our solar system as a whole. First, large bodies have orderly motions. For example, all the planets orbit the Sun in the same direction and in nearly the same plane. Second, planets fall into two major categories: the rocky terrestrial planets that include Mercury, Venus, Earth, and Mars, and the hydrogen-rich Jovian planets, Jupiter, Saturn, Uranus, and Neptune. Third, vast numbers of rocky asteroids and icy comets are found throughout the solar system, with asteroids concentrated in the asteroid belt between Mars and Jupiter, and comets concentrated in the Kuiper belt beyond Neptune and in the far more distant Oort cloud. Fourth, there are a few notable exceptions to the rules. For example, Uranus rotates almost on its side, and our moon is surprisingly large compared to Earth. The nebular theory explains all four features as consequences of the natural processes that accompany the birth of a star. Here, we see a very early stage in the formation of a star system, in which the cloud of gas that will become a star and planets is still large and diffuse. Because interstellar clouds are known as nebulas, we refer to the cloud that gave birth to our own solar system as the solar nebula. The red arrows indicate that gravity acts to make the cloud contract in size. Three key processes shape the solar nebula as it shrinks under gravity. Conservation of energy causes the nebula to heat up as gravitational potential energy is converted to thermal energy. The cloud becomes hotter near the center, where the Sun will form. Conservation of angular momentum causes the cloud to rotate faster as it shrinks. And the cloud flattens into a disk, a result of the averaging of velocities that occurs as gas particles collide with one another. Together, these processes explain how the solar nebula became a spinning disk with orderly motions, thereby accounting for our first major feature of the solar system. Now consider this question. Based on what you have seen so far in this video, which of the following statements should be true about spinning disks of material around other stars? Is it that their disks should be much hotter than the one that formed around our Sun? That their disks should rotate much faster than the one that formed around our Sun? That few, if any, other stars should have such disks when they are forming? Or that most or all stars should be surrounded by spinning disks of gas as they form? The answer is D. We expect the same processes of heating, spinning, and flattening to occur as other stars form from collapsing gas clouds, so they should also be surrounded by spinning disks. That is a major reason why the nebular theory actually predicts that planets should be common around other stars. The full disk diameter was probably about twice that of Pluto's orbit today, but let's zoom in to the region in which the planets formed. The hydrogen and helium that made up about 98% of the nebula remained gaseous, but other materials began to condense into tiny solid particles that would serve as the seeds of planet formation. In the inner solar system, the warm temperatures allowed only rock and metal to condense. Farther out, beyond the frost line, it was cold enough for hydrogen compounds to condense as well, forming particles containing ice as well as metal and rock. Because hydrogen compounds were about 3 times as abundant as metal and rock, the total amount of solid material was much greater beyond the frost line than within it. The solid seeds gradually accreted to form larger planetesimals. The planetesimals of the inner solar system were made of metal and rock, which explains the composition of the terrestrial planets. In the outer solar system, planetesimals grew large enough for their gravity to attract and hold hydrogen and helium gas from the nebula, which formed spinning disks, much like that of the nebula as a whole. The Jovian planets formed at the centers, ending up made largely of hydrogen, helium, and hydrogen compounds. Moons formed in the surrounding disks, and the icy composition of the outer solar system planetesimals explains why these moons tend to be icy. After the nebula was cleared away, the solar system was still filled with many leftover planetesimals. Some of the largest of these caused giant impacts thought to be responsible for many exceptions to the rules. For example, substantial evidence suggests that our moon formed as a result of a giant impact. Many more leftovers crashed into planets and moons, particularly during the solar system's first half-billion-year period that we call the heavy bombardment. The leftover planetesimals that remain to this day are the asteroids and comets, and we'll discuss elsewhere why these ended up concentrated in the asteroid belt, Kuiper belt, and Oort cloud. We have now seen how the nebular theory explains the four major features of the solar system, which is one reason this theory is widely accepted. In addition, the theory has had many predictive successes, perhaps the most impressive being its prediction that planets should be common around other stars, a prediction that has been spectacularly verified over the past couple decades. While these extrasolar planetary systems have revealed some surprises that have forced scientists to revisit details of the nebular theory, there is little doubt that the theory explains the general way in which stars and planets form.